my talk will be mainly structured into three parts. First of all, I would like to introduce you to the setup of our research initiatives and how simulation-based optimization can be coupled in a meaningful way for challenging tasks concerning simulations with high runtime consumptions, and finally one example of a project which we did in related to design optimization. So our research group named Heuristic and Evolutionary Algorithms laboratory exists for 15 years at University of Applied Science, Upper Austria, but the origin stems back to the Johannes Kepler University, where also the development of the software infrastructure with which we are still working had its starting points. Yeah, and one issue maybe is that all our research projects are third-party funding. Therefore, we are pretty close to the applications, because we also have the permanent need for presuming work with third-party funded project, which we did over the last years, is mainly based on Josef Ressel Centers, which is the University of Applied Science pendant to the Christian Doppler labs, and we also had the opportunity to run a COMET project in this area. So our core topic has ever been and still is the research in also algorithm research in the field of metaheuristics. For those of you who are not familiar with these topics, metaheuristics are stochastic search techniques which usually come into play if there is no mathematically exact method which can fulfill the needs in proper time. Examples are combinatorial optimization problems with exponential growth behavior in terms of solution alternatives, but also in the field of machine learning for complex search tasks in the spaces of hypotheses. But due to its incompleteness with respect to search strategies, those generic techniques are often compared with the search for a needle in the haystack. The only different thing is that in our haystacks there are many needles, but some of them are more maybe bronze, some of them are silver, some of them are gold, and some of them are platinum, and we are looking out for the better needles with a reasonable amount of trials. Often the search spaces for combinatorial optimization problems in practically relevant dimensions may be in the order of magnitudes of 10 to the power of several hundreds, or even 10 to the power of several thousand solution alternatives. And if our parallel hardware infrastructure allows us maybe in a night run to have 10 to the power of 7 solution candidates, it's very narrow search, and we need somehow intelligent strategies to consume this budget as good as possible. And one consequence in this research field is the no free lunch theorem of optimization, which more or less tells us that there must not be any algorithm that outperforms all others in arbitrary problem situations, or stated otherwise, it always depends on the characteristics of the problem and its search space characteristics, which algorithm strategy comes to mind, which should be indicated here. On the lower level, we have exemplary problem instances, and on the upper level layer, we have algorithm classes and algorithm instances. And it's often very much about choosing the right algorithm instance for a concrete problem instance at hand. And this was at the same time for us, the initial point of motivation to start with a software framework, which we called Heuristiclab, because if you cannot know in advance which algorithmic strategy to choose, or even worse, if there is a standard algorithmic strategy for a problem at hand, it might be somehow a little bit dangerous to start from scratch every time. And from our perspective, that's somehow some ideal point for having a bunch of solution alternatives for rapid prototyping or comparing algorithmic approaches, or maybe also see that there is no standard approach. There's a need for hybridization of different algorithmic strategies, and so on and so far. And that's the core point of research interests, which is summarized in the Heuristiclab framework. For those of you who are interested in, it's open source. You can give it a try. There are video tutorials on YouTube and so on if you're interested in the stuff which I'm showing you here. And over the years, enriched with each master thesis, with each PhD project, also new algorithms and problem instances came into play. And from this core part, there are different application sites here. I start with the machine learning part, where those kinds of algorithms are used for search algorithms in complex hypothesis spaces. Our special field of research interest is white box machine learning here, with symbolic regression models, which are interpretable and explainable, but are limited to structured numerical data because they produce mathematical formulas, nonlinear mathematical formulas, which internally expressed as syntax tree, mostly with evolutionary algorithms as search strategies. Mainly genetic programming comes to play here. Another area of application, which I would say is the most traditional application of metaheuristics, is optimization issues in production and logistics, where we also touch and cover the field of operations research. And the youngest field of research is coupling those kind of optimization strategies with the field of modeling and simulation, where the aim often is that the abstract formulation of a combinatorial optimization problem turns out to be too high level, too abstract, and with an appropriate simulation model, you can model more details. But on the other hand, if you want to use this for optimization issues where the run of a single simulation model is just the evaluation of a solution candidate, runtime becomes a very critical issue, because the runtime consumption of a simulation model is far higher than just evaluating a term. And which will be a main topic in my talk, and which also builds the bridge between the right and the left part, because often it turns out to be good enough to have some data-based model as a guess for the runtime intense simulation model, in order to state that maybe a solution candidate is not interesting at all. Therefore, we were often not interested in the exact objective for a solution candidate, and only if it becomes more and more interesting, if we are approaching more and more interesting regions of the search space, we use the expensive simulation model. That's more or less the idea. Here are some key facts about the Heuristiclab environment. Version is now 3.3.16, so 2 times we restarted from scratch. Unfortunately, there has been the need in this development story, and well, runtime, as already mentioned, is often an issue. But in contrast to neural networks and deep learning, our runtime environment is mainly CPU clusters and not GPU clusters. And therefore, we tried, if the projects allowed, also to build up some high performance cluster with CPUs. And at where we are standing at the moment is that we can use around 1,000 cores also including students' labs, which are used overnight and over the weekend for heuristic lab runs. And as already mentioned, it's open source, at least its basis functionality, and you can feel free to give it a try. And over the years, many algorithms have been implemented for combinatorial optimization, for data analysis, and even if heuristics have many features which are not so nice, one nice feature of Metaheristic is that they are generic. So you can basically use the strategy. It's not clear if it will be successful, but basically you can use it for arbitrary problem situations, and therefore you have many degrees of freedom to combine algorithms with problem situation. When we had less algorithms, the algorithms and the problems could be placed on one slide, and then we could say it's almost a fully connected bipartite graph, the combinations which are here. But luckily, I have to say, over the years, more algorithms have been implemented and also more problems have been tackled, and therefore we have it on two slides now. I will not go into detail about this, just tell you if it might be useful for you, you can give it a try. And well, we have been discussing a lot internally also in the group. It's even it's a good idea or not to go open source. Finally, we decided yes, because most of the funding came from the public, which has allowed us to implement this kind of stuff. Therefore, it's somehow also fair to provide it to the public. But frankly speaking, mainly we developed the framework for our own purposes and not so user friendly as you would really provide it to the public. And even more, we have been surprised when we have been analyzing 2 years ago the spreading of use of Heuristiclab in the scientific community worldwide, where we did an analysis and even excluded the networks of JKU and University of Applied Science, where we use it for teaching issues more heavily. And we were surprised ourselves how many users there are, because regularly we do not observe, we just see requests in the Google groups or so, but no clear analysis about this. Okay, here are some details when you want to try it out yourself, but now I want to go more to the topic of the talk, starting in this corner with the machine learning approaches, with the white box machine learning approaches based on structured numerical data. How we used to do it was symbolic regression based on genetic programming as such technique for our models. So white box models mean that the input variables are transformed to one or more output variables, can be interpreted by the user, which has some pros and also some cons, of course, compared to black box models. One disadvantage of our white box approach is that we are limited to structured numerical data, typically sensor data, sensor values. But the advantage is that on the one hand, you can interpret the model outcome together with a domain expert. You can get closer to questioning causality in the models. You can also somehow hybridize a priori knowledge with data-based knowledge. So there is not a contradiction whether to go an natural science-based way or to go a data-based way. It can also be combined in some way, and those and typically, as we have seen over the years, those kind of methods appear to be especially suited for modeling systems with a strong background in natural science, where the mathematical language can be somehow seen as the, say, natural language of describing things. Well, here you see some example model, simple model, how it may appear as a symbolic expression, here indicated with a scatter plot, where the points which you can see, the better the model on the training or on the validation on the test data, the closer you are at the fixed point line, the 45-degree line, as typically expressed in a scatter plot. But obviously, we are facing also many challenges here. It's not that easy. You should go for a more compact model because they are easier to explain, they are less likely to overfit, and so on. And often, as we all know from basic mathematical courses, it's far from being unique how you can express things with a mathematical formula. For example, this mathematical expression gives you this nice shape of a curve, but this formula is almost the same shape of the curve, and also there are many different ways, if we transform mathematical terms, to have exactly the same formulation for a certain output of the formula, which is also an issue which has to be considered internally in the algorithm, for example, to avoid so-called phenomena of code bloat and introns, which means either totally meaningless expressions which might also appear due to the stochasticity of the search process, or terms which are far more complex than they could be expressed in a more concise formulation. So those are research topics which are typically matter of research for our PhD students in this field. From the basic idea of search, genetic programming comes into play as, let's say, the standard algorithms for searching in space of nonlinear models expressed as syntax trees. It's a so-called population-based approach, so we have many candidate models starting with arbitrary syntax trees, just giving a formal grammar which terminal nodes to use, usually the coefficients, the variables, the constants, and which inner nodes to use. Here you can see which mathematical expressions you want to provide for the expressive power of your space of hypotheses, and then the evolutionary process comes into play by repeatedly applying selection, which selects above average models in the parent generation, and then crossover, which recombines two above average parent models to a common offspring, to a child individual, which is sometimes being mutated in an arbitrary way in order to maintain genetic diversity in the population. And then we have to decide which of the offspring models will be allowed to become parents themselves, which can be done in the offspring selection step. And then after filling many offspring to the next generation, one iteration is done, and this process is repeated again and again, often for thousands of generations, which can also make it quite runtime intense, especially in the case of higher dimensional problems. But just to show you the idea on a, say, toy problem, but I think it's a good way of seeing some properties when we see the curve to be approximated here with the small axis, and we see a starting population of arbitrary random candidate models with input variables where we think that they might be meaningful to model the system's behavior. We can see how the optimization process tries to reduce the errors on the training data and comes to models which fit the system's behavior better and better over time, which we can see in this small video. And on the bottom you see the formula which is applied at the moment, which is the best solution candidate. The larger amplitudes are optimized earlier, and then the smaller deviations come into play. And another illustrative picture here from an artificial benchmark problem, which came from a competition of a conference, just to show you the way, on the one hand, how such a model is internally expressed in a syntax tree, where we have the mathematical functions as the inner nodes of the syntax tree, and where we have the variables and the coefficients as the leaf nodes of the syntax tree. And if we show the syntax tree in a standard way of a mathematical expression, I think one can easily imagine that together with a domain expert, it becomes possible to analyze whether or not the identified correlations turn out to be really useful, maybe even sometimes surprising, maybe sometimes even contradictive. Then one may take a closer look about the input data, if everything's correct, or maybe even misleading, or such tasks. Of course, what we can see here on this picture is somehow a little bit idealized. It's a already very compact formulation. In reality, the model outputs are often rather gray box than white box. Therefore, we also had some strong investigations over the years to have in some semi-automated way with user interaction, giving the user the possibility to simplify the models somehow by hand, or somehow also in an automated way. For example, here what's indicated in shades of green or red or neutral is the impact of subtrees, and the user, by double-clicking, for example, a subtree, which can even be counterproductive, as indicated here with the red subtree, can be simply switched off. Also, there can be some symbolic simplification, because the genetic programming task doesn't care about how the building blocks are recombined. There may be meaningless expressions which can be easily put together, and also gradient descent methods can be applied on the coefficients to optimize the coefficients with respect to a given model structure in a post-processing step. But this can also be included into the algorithms. But just to say you that this nice white box behavior often needs some additional effort before such a really compact formulation can be presented as an output. So this was the right part of the picture, the data-based modeling part, with a special focus on interpretability and explainability, by providing white box models on structured numerical data, typically sensor value. And now I want to make the bridge to the sorry, too fast. I want to make the bridge to the simulation part on the other side of the picture, where, especially if the real simulation is too costly, too runtime intense, the question is, how can we hybridize in a clever way the data-based model as surrogate models for the expensive simulations. From a technical perspective, inside our software system, one block in this plugin infrastructure is the evaluation operator, and which is usually done internally, but can also call an external simulation model, like, for example, some simulation environment like any logic. For those of you who are interested in technical details, we are using Google Protocol Buffer as transfer protocol in order to call a simulation model as an external evaluator, which evaluates a solution candidate, a scenario maybe, and gives back the objective value, or for multi-objective optimization issues, the objective values of a solution candidate. That's one way of approach of simulation-based optimization incorporating heuristic techniques. Another way is that maybe within your simulation some optimization task appears, and from the simulation an optimization is called, which returns back the optimized solution to the simulation models, which are basically two ways of approach in simulation-based optimization. For the surrogate-assisted optimization approach, it is rather the first way, where the optimization is somehow the master process, which uses simulation for estimating the quality of solution candidates, especially when the real simulation becomes too runtime intense. And the variety of runtime consumption is often pretty huge in discrete event-based simulation. Well, it's sometimes in the area of seconds maybe, which is bad enough for task, but it can even become far worse if we have finite element simulation models, which are even more runtime intense. Then efficient parallelization will not be enough to use capable search techniques, and latest at those points the hybridization with surrogate models becomes a very important issue to evaluate many solution candidates, not with the expensive simulation, but with the surrogate model. So the idea of surrogate model is that we learn from data a model which approximates our real behavior, for example of the simulation model, and the more dense our observations are in some areas, the more trust we can have to the surrogate model. So it's a real question of database and the quality of database, how good this approach will be likely to work. Basically can be done offline, that we have the machine learning parts totally offline based on data which have been created earlier by the simulation as training data. But it can also be done hand in hand, that during the optimization process, where we identify how interesting the area of search is already been, the modeling task is carried out online, and also even those ways of approach can be hybridized. Here, some very high-level illustrative picture where we have the optimization part on the one side, and as shown before, the evaluation of solution quality, the fitness evaluation, would be done with a simulation model, which might be too runtime intensive, and then could be done with a surrogate model. Or I would even draw an additional line, because it can be coupled also, sometimes done with the simulation, or in the ideal case, the expensive simulation, only to validate solution candidates which have been optimized in such a way of approach, which has been showing here for the online part, where the machine learning parts learns during the optimization process for candidate models. Basically, this way of approach can be combined with many machine learning algorithms, not only symbolic regression, of course. It could be done also with random forests, which are often pretty robust. It can be done with linear regression, polynomial regression. Also, Gaussian processes are somehow very interested with respect to some features they offer. Also, black box methods like neural networks can come into play. So basically, we are not really limited in the way of machine learning methods we use. Also in our research works and publications, also to be more or less fair in terms of comparison, we often compare different machine learning approaches, even though our special research interest belongs to symbolic regression on white box models. And considering the basic ways of approach, we can distinguish between those two types, where on the one hand, the creation of the surrogate model, the modeling, the machine learning approach can be either done offline or online during the run, which is shown here exemplarily for Gaussian processes, or Kriging approach, how it's often called here, where here on those points we have evaluation with the expensive simulation. So for those points we can really trust that the model output is where we have our approximated output, and depending on which kernel function we use in our Gaussian processes, we have some levels of uncertainty between the points, and the less the density of points which have been evaluated with the exact model, with the simulation model, the more uncertainty we have. For example, here we have a quite huge area which outputs which are not too far from each other, and therefore we really don't know a lot about the shape of the curve inside here. So there's a large area of uncertainty, whereas here the area of uncertainty is lower because we have already more sample points. And for the online approach, an interesting question is to identify promising points where we can evaluate the next point with limited budget. So because the simulation is very intense, for example, if we want to use expensive, like a expensive simulation, like a finite element simulation, we want to evaluate on points which are most promising. And for example, if we consider here the point at 0.8 on the horizontal, then we have this guess with our concrete kernel, let's say. So this guess is would be worse than the best solution found so far with the exact simulation. And here for the Gaussian estimation, we have this rosé shaded area of the Gauss curve, giving us the probability that on the point 0.8 there might be a solution even better than the best solution found so far. And for identifying the next point to be evaluated, this is one argument for the selection of the next point, and another argument is to minimize the areas which very loose sample points, which would typically be somewhere in this range where we want to, where we have a lot of uncertainty, and with going for one compromise, and if this compromise is identified, then we jump to the other compromise to better scan regions which have not been scanned so far, which typically gives us this kind of expected improvement function. Here, it would be a dominant feature to better explore the unexplored region. And then if we would do so, these areas of uncertainty would become far less, and then the greediness aspect would come more into play. So it's somehow the old interplay between intensification, greediness of search, and exploration behavior of supporting global search behavior. Here, this decision would have been for the global search behavior. Those expected improvements would rather be for the greediness. So, and with this setup, I come to the concrete projects where we have been invited for the optimization part in a COMET project. It was about box type boom optimization, where in the consortium there were groups which with a certain expertise in the finite element simulation model, which has been used for the design optimization of box type booms. Optimization issues for this task is to reduce the costs, of course, material costs and welding costs concretely, but under certain structural constraints. In this case, it was stress, fatigue, and buckling. And the evaluation of those constraints really took a lot of expensive simulation time of finite element simulation, and that's where the surrogate-assisted modeling approach comes into play in this example. So finding predictors for stability have been learned mainly offline here with arbitrary point, but also hybridized with already points from optimized areas of the search space, because that's of course the area which is of more interest. So what we did here was even say some kind of hybridization between the offline and the online approach, where the arbitrary chosen points are of course easier to parallelize because this can be done offline. So there are certain variables for each segment of the box type boom, which appear as input variables. So overall, it was 8 models, 3 for stress, bottom, sides, top, the same for fatigue and for buckling too. So overall, for each part of the box type boom, for each segment of the box type boom, say 8 models, and for more segments, n is the number of segments here, h times n, dimensions of the vector to be considered for learning the surrogate models. And here you can see one of those surrogate models which turned out to operate surprisingly well, as could be published here in this publication from last year. So model qualities were in the range of, if I remember correctly, Pearson R squared of more than 0.99, so pretty good estimators, where it was often good enough to use the finite element simulation or only for verification or for validation of learned results to fulfill the constraints. Sometimes, what was also interesting for those outputs, I don't remember exactly which it was, that they could take profit using virtual sensors as inputs from other models, which at second thought definitely makes sense if we think about the segments and how they interfere with each other. But nevertheless, it was an interesting observations. And if we succeed to do so with white box models, there are some additional benefits which can be made easier, transparent, like for example the impact of variables as it can be seen here, where we have our 8 models on the vertical and the variables on the horizontal, and then we can see the certain impacts which are calculated in a way that we question how modeling quality would decrease if we would take away a certain variable. And another point which is interesting to observe for models anyway, but especially for white box models, when we have in the post-analysis stage the question which model really to trust and which model to use to analyze partial dependence plots, where the user can interact actively with the models and here see how the other variables behave. If I shift one variable, are they positively correlated? Are they negatively correlated? Are there some numerical effects like poles or so, which we would not like in the phase of extrapolation? For example, here we see the red shaded areas, which are typically extrapolation areas. Here we see indicated the density of observations in some certain areas, so it will be easier to model. We have less interpolation error probability if we have dense observations in this area, as we can see here, and it's nice for the domain expert to have this opportunity to play around with the model, also to see will I trust the model? Do I want to apply it in practice, or there may be some dangerous effects, numerical behavior, like say e to the power of some nominator and dominator, where the denominator can get close to 0, where under certain inputs, typically numerical effects. And if we use ensemble models or Gaussian processes, which somehow allow us to estimate the level of uncertainty, or in a loose interpretation, we could also call it confidence, then we can also see the area where models could be, the model output could likely be. So we have more or less, for example, for random forests, the majority model, but also the range of models where they could be. And of course, the more dense our observation in a certain area, the less uncertainty we have, and the lower the density of observations, the higher uncertainty can be, which are all some examples of how to bring extra insights to the domain expert in order to have more trust in the data-based models. So this was it from my side for the talk, and of course I'm happy for questions.
Okay, thank you very much, Professor Affenzeller, for a very nice talk. And now it's open for questions, please. So you can switch on your microphone.
Hi.
Hi.
So just a short question from my side. Thank you very much for this presentation. That was really, really globally capturing the evolution in the field, actually. So with regard to the example that on the crane that you showed, you mentioned welding, and you also measured material cost. So can I ask if you were given some physical models about this welding, and did you find them very expensive to simulate? Did you find them challenging to implement in your optimization platform?
So the costs, which were material costs and welding costs, were those costs to be optimized. So for our part of the project, frankly speaking, this was the black box. This was provided by the finite element experts, and our task in order to make optimization possible was to find the surrogate models with the machine learning approaches. So if you are deeper interested in those effects, I could provide you the contact details of our project partners which were responsible for that task.
Okay, thank you very much.
Thank you very much. Yeah. A further question, please. So as far as I can see, there is no further question anymore. Everything is clear. So I would like to thank you again, Professor Michael Affenzeller, for a nice talk. Yeah, thank you very much.
Okay, thank you for the invitation.